Hello, gentlemen. Welcome to another Pallavi Market Research video. Today, I'm going to be discussing how to master probability and to ultimately use probability and the mental models that come from understanding it to transform your decision-making skills. Now, in order to learn how to think in terms of probability, you have to understand the difference between thinking in terms of probability and thinking in terms of possibility. Most people, they don't think about what is the most likely event. They think about the most painful possibilities or the most pleasurable possibilities that they could possibly go through. Everyone who thinks in terms of possibilities is driven by their emotions. They have an emotional bias towards the possibilities that they give the most time to mentally. Okay. So you have to first understand when you are thinking in terms of probabilities versus possibilities. And you don't want to prioritize thinking about possibilities because they all have an emotional bias towards them. Okay. And especially in the context of investing, but this applies to every area of your life, relationships, business partners, everything. Okay. But we're going to obviously prioritize thinking about this in the context of investing today. And in order to do this, in order to think in terms of probabilities, you need to be able to see patterns in data sets, right? So that is why in this video, we're going to be discussing common probability distributions so that you can better see through the patterns in the data sets you are engaging with. Okay. So when you have a probability distribution and you receive a data set, you are at a binary decision. Is this a discrete probability distribution or a continuous probability distribution? Okay. And if it's discrete, then you are basically dealing with a countable and distinct random set of numbers. Okay. Whereas if it's continuous, you're dealing with infinite numbers within a given range. So, for an example of continuous, it's like people's height or the amount of rain in a city in a particular time of year, right? You have a ton of data, almost an unlimited amount of data to see how many times it does it usually rain on this day per year in this city, right? And then back to discrete, this is like if you have 10 coin flips, how many of those coin flips are heads or tails, or the number of red cards shown in a deck. So just to visualize these for you, we have the binomials, the Poisson, the normal, the uniforms, and these are all color coordinated so you can understand what these actually look like when we are visualizing the data. Okay. So, like we were kind of just touching on, a normal distribution is a simple example of weekly temperature fluctuations within X given zip code over X period of time, right? So it's for measuring natural phenomena that we have huge data for. A T distribution is a little bit different. This is for measuring the effectiveness or scoring the effectiveness or confidence of a new drug based off of some small clinical trial, right? So it's something that approximates a normal distribution, but isn't able to achieve a truly normal distribution like you can see with these green and blue lines because we are limited in data and we have a very uncertain variance. Okay, so if you're seeing this distribution, you're most likely seeing something with limited data. Okay, so a binomial distribution kind of goes back around to the a 1 or 0 type of testing. So it's, do I have green eyes? Do I have blue eyes? Did I flip heads? Did I hit tails? Did I generate a 1 or a 0? Okay, that's a binomial distribution. Binomial by, right? I being 2. Okay, so a Poisson distribution, this describes the probability of any given number of events occurring in a fixed interval of time or space. So this is like what happens if two events happen in the same time period, right? So this is like very common for insurance agencies to use because if we use like Puerto Rico as an example in the house I'm in, if a home insurance company is like measuring the risk of me living here next to the ocean, they're like, okay, well, what if there's a hurricane? What if there's this level of hurricane? And what if there's a power outage that happens that week? And what if there's a tsunami that happens that same day, right? They take all of these extremely unlikely possibilities and then they have to measure whether how close that these things can actually happen on top of each other and what are the odds that multiple bad things happen within like a 2-month period, right? So this is insurance, risk management, right? Models the number of cars passing through a certain point in a given time, right? So there's typically a time constraint for these distributions. Okay. Log normal. This is really interesting. So a log normal is typically used in financial markets for modeling stock prices over time. A log normal distribution is preferred because stock prices cannot go negative. Hence why the distribution has allowed a rightward skewing in correlation with increased data. So we're comfortable with a log normal distribution having a continuous rightward skewing and not approximating back to a normal distribution like this, because because of the nature of the data, there's going to be some rightward skewing, and there's going to be rightward skewing because large positive returns are only possible because there are not equally large negative returns, because you can't have a negative return on your stock, right? It can't like go, it can't, you can have a negative return. You can't have a number go negative. No. An exponential distribution. This is probably one that you're very familiar with, but this is modeling the time you have to wait for the next event in scenarios where events happen independently and at a constant rate. So the time a high quality light bulb takes to burn out, or the time between bus arrivals, right? This is also used to measure Pareto distributions. And if you know what those are, good. If you don't, go learn. The law of large numbers. This one is one of the most important ones, okay? As you can see, the more data you have, the less variance you have in the mean, in your z-score. Meaning, the more data you have, the more accurate, the more reliable your data is, okay? The more your averages and means are actually valuable to you. Okay, this one's interesting. So this is kind of touching on a similar idea, the central limit theorem, okay? This is basically a sampling distribution of the mean, which will approach a normal distribution as the sample size becomes larger, right? So this is kind of what we were talking about earlier. As we increase our data, it will strive to look more like this and less like this purple blob thing, okay? So this is another way of looking at this, all right? If we have a population size and initially it has a normal distribution or uniform distribution or skewed distribution or random distribution, as the sample size goes up, right, n to 10, n to 30, it will always strive to look more normal. That is what the central limit theorem means. And obviously there are examples of this not happening, but this is generally what happens to data as your sample size increases, okay? Now, we're going to discuss random number distribution, but more specifically, random number generation. Because if you study the great quantitative hedge funds of the last 20, 30 years, you'll learn about Renaissance Technologies and John Simons and how these companies use trading algorithms to predict the stock market. Specifically, Markov chains, okay, that take random sets of data, right? And then they reverse engineer that data. How do they reverse engineer that data? Well, they use things like random numbers, okay, to create probabilities for different outcomes. But you can't really use a Markov chain really all that well if you do not have a way to generate random numbers. Now, I'm going to walk you through how a random number generator works and how it really generates random numbers from in the first place, okay? So really a true random number generator is generating something, a source. So like in this example, it's a photon source, right? Instead of a computer program, right? So computer programs are not considered truly random, okay? But we're going to talk about truly random number generators, okay? And in order to do this, you need a physical source of unpredictable natural phenomenon, aka you need a source of entropy, okay? So once you have an unpredictable physical process, entropy source, like short noise, okay, for example, this is the noise produced by the random events of particles kind of moving around, right? So like if they cross a barrier, right, they release a little bit of noise. There's also this example, which is a photonic entropy source. This is using beam splitters and single proton detectors, which allow you to measure a path of a photon and the path that it takes, and it allows you to scrape the data from that path. So if it skews right or skews down, skews up, that's a 1 or a 0, right? And then also just the random motion of atoms and electrons and materials can be captured as thermal noise, which can be used to generate random numbers, okay? So once you have a photon source or an entropy source, then you can start to actually convert that source of entropy into a random number, right? So, but in order to actually achieve that, you need all these other systems here like lenses, tunable polarizers, right? Photon detectors, coincidence counters, RNGs, right? So these are essentially amplifiers and converters, which often signal the if the entropy source is too low, so it like amplifies the entropy source, right? So it's able to be read and then measured and converted into a digital value. Because at the end of the day, if you were collecting data, you have to manifest that data through a digital value, 1, 0, right? Okay, so that is how the random number generator works. And if you understand these concepts, like I was saying in the beginning of this video, then you're going to be able to think in terms of, how do I want to say this? I want you to be able to see when you're looking at a data set, I want you to be able to see the pattern. I want you to be able to see the statistical distribution, the probability distribution that is likely sitting on top of this data set. So you want to understand whether or not this is a model that's utilizing random numbers, whether or not this is like, a something like a head or tails trial where like, hey, the more data we have on this, the better, or if this is always going to be data constrained like these binomials and these discrete probability distributions. Okay. I hope that's helpful. Not a little, I hope that wasn't too convoluted, but that's today's video. Have a great morning. We will get tomorrow. See you guys.